If you dig in just the right places, you can unearth skeletons that tell the story of past plants, animals, and humans. But finding preserved soft tissues, like the brain, well, that's pretty rare. I'm Alexandra Morton-Hayward, and I'm a forensic anthropologist. I'm trying to figure out why, despite all the biological odds being stacked against it, some brains, like this one, become fossils. The brain is a complex organ made up of neurons and other sophisticated cells, themselves made up of biomolecules like proteins, lipids, and metabolites that work day and night to ensure the brain and the rest of the body function. However, after death, the brain is one of the first organs to decompose. How then have some preserved over 12,000 years? Let's go find out. From a 2,500-year-old salt mine in Bronze Age Iran, to the shores of a lake bed in Stone Age Sweden, and to the summit of Andean volcanoes at the height of the Incan Empire. These preserved human brains represent a bewildering array of society, from Egyptian and Korean royalty to Arctic explorers, and from British and Danish monks to prisoners of war. Such huge variety in burial environment and timescale represents a challenge for understanding how preserved brains can persist when all other soft tissues are lost. I georeferenced excavation sites with paleoclimate data like temperature and rainfall to try to understand the environmental conditions that might have led to this exceptional soft tissue preservation. I found a range of burial conditions, including dehydration, freezing, tanning, which usually occurs within peat bogs, and saponification, the transformation of fats to graveworks, can all influence soft tissue preservation. These are changes we can see with the naked eye, but what's happening at the molecular level? We currently have a theory as to how and why nervous tissues preserve on geological timescales, which depends on the unique biochemistry of the brain itself. The cross-linking of molecules, where proteins and lipids fuse together, particularly in the presence of metals like iron and copper, is well known in diseases like Alzheimer's, and we think this might happen in the grave as well. While we're still studying how these mechanisms work, we've found records of thousands more ancient brains than was previously known, showing that fossilized nervous tissues are not as rare as we had imagined. These ancient brains provide unique insights into the long dead that the bones alone can't, shedding light on health, disease, behavior, and cognition throughout our human history.